Hello everybody. Today we will talk about measurements in quantum mechanics, and we will look into postulate 4 of quantum mechanics, which talks about the quantum measurements. To measure an observable A, consider the eigenvalue equation of the operator A. So there are two terms you are seeing, one is operator and the other is the observable. Any operator which you can measure will be termed as the observable. So let us say that we are trying to measure this observable given by A. So we can put an eigenvalue equation for corresponding to this measurement, which is given by A into eigenstate un equal to eigenvalue into eigenstate. So what is lambda n? Lambda n are the eigenvalues which this operator can have, because this is basically a matrix. So this matrix can have, let us say, n eigenvalues, and we represent those n eigenvalues as lambda 1, lambda 2 up to lambda n, and corresponding to each eigenvalue there will be an eigenstate. So corresponding to lambda 1 there will be an eigenstate given by ket u1, for lambda 2 ket u2, and so on. So therefore we can put this eigenvalue equation based on the eigenvalues and the eigenstates of this observable or the operator A. Now let us consider an arbitrary quantum state given by ket psi and is normalized such that the inner product of ket psi with itself is 1, which is a basic condition for the normalization. Now, according to Born's rule, the probability of getting a particular eigenvalue lambda n is given by the squared magnitude of basically the projection of psi onto the corresponding eigenstate, or we can say that it is the squared magnitude of the inner product of un with psi. So that's the probability of getting a particular lambda n. That's what is written. I'm trying to put as a in this paragraph, in this line, which says that probability of quantum state collapse to lambda n eigenvalue is equal to the magnitude square of the projection of psi onto corresponding eigenstate to the particular eigenvalue. So this eigenstate is particularly corresponding to this eigenvalue. So therefore, let us consider the eigenvalues of A. So eigenvalues are lambda 1, lambda 2, lambda 3 up to lambda n, and so on. So corresponding eigenstates are ket u1, ket u2, ket u3, and ket un, and you can if there are more eigenvalues we can have the corresponding eigenstates. So what is the measurement outcome? A measurement outcome, as we know from Born's rule, that we can get the probability of getting this particular lambda 1, let us say. So it is given by the magnitude square of the projection of psi onto eigenstate u1. Similarly for lambda 2, this projection of psi onto u2, magnitude squared, and so on. So we can say that the measurement outcome in quantum mechanics is probabilistic in nature. So to carry forward the discussion, let us imagine multiple copies of the quantum system, that means quantum state ket psi. Let us assume we have n copies, capital N copies, rather than having only one copy, and we measure capital A, that means the observable A, for all copies. So what we see here, let us say for first measurement we get an eigenvalue of lambda 10. Second measurement we get an eigenvalue of lambda 1, lambda 19 third time, lambda 10 fourth time, and so on. So we will get different values of the outcomes That means number of times and a particular eigenvalue appears, so we will get that number for each eigenvalue. And we can also calculate the probabilities. So how? We can also calculate the experimental probability. So say we get lambda n, which is the eigenvalue Pn times. So how many times we are doing the measurement? Capital N times, total number of times, and we are, let us say, get lambda n Pn times, or you can say that lambda 1 3 times, lambda 2 4 times, and so on. And let us say total number of measurements that we perform are 100. So definitely capital N will be equal to 100, and Pn will be the number of times a particular eigenvalue appears during the measurements that we are trying to perform. So as per central limit theorem, when capital N is going towards infinity, this experimental probability, which is number of times an eigenvalue appears divided by the total number of measurements for lambda n, will be equal to the probability of lambda n given by Bond's rule, which we may say as the theoretical probability as per Bond's rule. So in quantum mechanics tells us exact rate at which we get a particular lambda n when capital N approaches infinity. Now we can express this quantum state as a linear combination of the basis states, where Cn are the expansion coefficients, cat Un are the eigenstates or the basis states. So cat psi is a summation of the eigenstates and the coefficients for a particular eigenstate, expansion coefficient. And we know that this coefficient is given by the inner product of Un with psi, of a particular eigenstate with psi. And we know that the probability lambda n is, as per Bond's rule, is given by the squared magnitude. So if we just replace Un's inner product Un psi with Cn, we get the probability of a particular eigenstate as mod Cn square. As a special case, if let us say the quantum state that we have selected is the eigenstate itself, in that case the coefficient will be equal to 1, and because we have already selected a particular eigenstate, that means the quantum state is already in a basis state, so therefore the probability of the eigenvalue corresponding to that eigenstate will be equal to 1. That's a special case. Now let us look into postulate 4. When we perform a measurement on a quantum system, the possible outcomes correspond to the eigenvalues of the Hermitian operator associated with that measurement. When we perform a measurement, the possible outcomes correspond to the eigenvalues basically of that observable, and that observable of course will be Hermitian operator. Why there is a requirement of the Hermitian operator? Because the eigenvalues of the Hermitian operator are real. Since we are measuring the property of the quantum system, and therefore the Hermitian the property that we are trying to measure must give a real outcome. So therefore it is a condition that the observable matrix must be a Hermitian matrix, because the eigenvalues of the Hermitian matrix will be real. The state of the system after measurement collapses, right? From superposition to a collapse takes place, and what is the resultant state? The resultant state will be the eigenstate corresponding to the observed outcome, which is basically the eigenvalue. So the quantum system or the quantum state will land itself into one of the eigenstates. Which eigenstate? For which we have obtained the maximum probability. Now in postulate 4, we are making the following assumptions. We are saying that the quantum state is normalized, that the eigenvalues form a non-degenerate spectrum. Now what is non-degenerate spectrum? All eigenvalues are distinct, meaning by if an eigenvalue has more than one eigenstate, that means a particular eigenvalue, if it has more than one eigenstate, so that will be termed as a degenerate spectrum. And we are assuming that every eigenvalue is distinct, meaning by every eigenvalue has a distinct eigenstate. So eigenvalues form a distinct spectrum. So let us look into this spectrum. Along the x-axis are the eigenvalues, along the y-axis are the probabilities of the particular eigenvalue. Let us say for lambda 1, we get, what is the probability of getting lambda 1 as the measurement outcome? It is mod c1 square, mod c2 square is the probability of getting lambda 2 as the measurement outcome, and so on. So basically we obtain a kind of probability distribution. So higher the height of a particular spectral line, the higher the probability. The higher the height, the more likely we measure that eigenvalue. So let us look at assumption 1, which is basically the normalization condition, which says that inner product of psi with itself should be equal to 1. Let us try to prove it. Let us try to look into this assumption in little more depth. We know that ket psi, as I have just explained, we can express ket psi as the summation of Cn ket un, which is the eigenstate. So ket psi is basically written like summation Cm. We are taking two different indices and we will afterwards equate the index. Let us see how. Since the first part is the bra of psi, so therefore this part is the bra of psi with index n, and this part is ket of psi with index m. And if we can take Cm from here, so Cn conjugate, so we can put it like this, and this will be the inner product of un and um, which is the Kronecker delta. So this Kronecker delta will be equal to 1 when n is equal to m, otherwise it will be equal to 0. So therefore when n is equal to m, so the summation reduces to one index. In that case, let us say the reduction is to index n, so therefore we get summation of the normalization condition is equal to the summation of all the probability values, right? So of course all the probabilities will go to 1, so therefore this is normalized. So this is how we can prove the first condition. However, if psi is not normalized, if psi, let us say, is not normalized, in that case the inner product will not be equal to 1 but rather a number, a value which let us say is capital N, and then the probabilities don't add up to 1. In order to ensure that probabilities do add up to 1, we may have to do the normalization. In that case, we will have to divide the probability with this with the norm of the quantum state to get the normalization condition. Now there is a theorem which explains the spectral eigenvalues. Like that theorem is spectral decomposition theorem. In quantum computing, degenerate eigenvalues and their projection operators play a significant role in understanding measurement. In understanding measurement, quantum observables and state space structure. Now let us say that we have an observable A that belongs to the Hilbert space H. Set of AIs are the set of eigenvalues, set of AI ket AIs are the corresponding eigenstates. So the spectral decomposition theorem So let us here let us not take the case of degenerate. Let us continue with let me make a brief change here. Let us continue with non-degenerate degenerates eigenvalues. So those eigenvalues for which the every eigenvalue will have a distinct or a unique eigenstate. So in that case, the matrix A will be equal to the summation of the projection operator multiplied by the eigenvalues. So what is projection operator? Projection operator for psi is given by the outer product of psi. That I have discussed in a different video. So you can look into different video to know about what is the projection operator. So what is spectral decomposition theorem? What does it state? It states that the matrix A can be expressed, or the observable A can be expressed as the summation of the product of the eigenvalues and their projection operators. Thank you.